Hey, good morning, everyone. So purpose of today and Wednesday is just going over a summary of most of the topics that we've covered, talking a little bit about the final, some of the expectations that I might have of you. It's also a really good opportunity for you to ask me questions if you have any concerns or you're wondering things about the final, like now and Wednesday is a good time to ask them. So today we are going to cover the first part of the course going up to week 7, pretty much. And then on Wednesday, we'll do weeks 8 to 12. Okay, before we get started, does anyone have any more general questions about the final? None? Yes, one. Aiming for about 8 or 9 questions. Again, there'll be multi-part questions. You should probably have a bit more time than you had on the midterm for these, because it's a 3-hour exam. Midterm questions, you had 3 for 45 minutes. You're going to have 8 or maybe 9 for 3 hours. So they might, some of those questions obviously might be a little bit longer because they'll be multi-part, but I think it will be a little bit slightly more relaxed pace is what we're aiming for. Okay. Any other questions? Okay. So I'm going to start by just summarizing some of the materials. So we started off in the first few weeks talking about matrices and vectors, and we introduced the idea of a vector and a dot product. You guys will be very familiar with vectors now, but remember with the vector we have this notation here, arrows over the top, and this represents the dot product between 2 vectors u and v. So if u is some vector, the components say u1, u2, and similarly for v, v1, v2. If we take the dot product of these 2 things, then all we're doing is we're taking the sum of the component-wise multiplication. Okay, so we multiply the first element of u, we'll call ui, times by the first element of vi, and sum that up. So this is just u1, v1, plus u2, v2, and so on. Okay. We also covered some relationships between the dot product and the angle between these 2 vectors. So if you have vectors u and v, angle between them, you say that u dot v is equal to the length of u times by the length of v times by the cosine of the angle between them. Okay. Now, I'm not going to require you to remember things like this formula here. If you need it, I'll put it on the formula sheet, okay? But it's just a refresher that this thing exists. Okay, so vectors and dot products, they were able to tell us things about, say, how we talked about antigenic evolution of viruses, for example, and we could represent the reaction between different antisera and different strains of viruses as a point in a space or a vector within some space. This could have any number of dimensions that we want. And then looking at things like the dot product or the distance between those vectors or distance between points as well could tell us something about the similarity between different strains or the direction of evolution. Okay, so that was that. We then moved on to matrices. Matrices we've used extensively. I'm not going to give a huge summary of them, but if you remember, if we have a matrix, a 2x2 matrix, which is most of what we've been dealing with entries A, B, C, D, then we had various things like the trace, which we often call tau, which is just the sum of the elements on the main diagonal. We also had the determinant, which was the product of the elements in the main diagonal, A times by D, and then subtract the elements on the off diagonal. It's our determinant. And then we can use the trace and the determinant. We've used those extensively later in the course when we'll be talking about linear systems and non-linear systems of ODEs and trying to understand the stability of, say, an equilibrium. But we can also use this to find the inverse of a matrix. So if the determinant is non-zero, Then we define the inverse of a matrix, A, equal to 1 over the determinant. This is for a 2 by 2. We switch the order of the elements on the main diagonal. So instead of A, we have D here. So of D, we have A there. And then we take minus the elements of the off diagonal. We don't change the order of the elements of the off diagonal, okay? So this is the inverse of A, and we have the property that if we take a matrix A, multiply it by its inverse, we get the identity matrix. The identity matrix is just ones on the main diagonal and zeros on the off diagonal. Okay, welcome back, everyone. No one set off the fire alarm again, please. Okay. I am going to go through these things a little bit quicker so we can deal with some problems. After matrices, well, just one more thing on matrices. We talked about solving linear systems. The reason we look at inverses is if we have a problem that looks like this. We have some matrix times by some unknown vector is equal to something that we know. We can find out that unknown vector by taking the inverse of that matrix times by our vector on the right-hand side, okay? We also talked about population models. We've seen as we've done those recently with compartment models. I will skip over that for now. We've talked a lot about partial derivatives. Hopefully you guys can remember how to do that. Remember, you're taking the derivative with respect to, say, x, if you have a function f of x, y. We treat the y's as constant when we take our partial with respect to x. So y is constant, and vice versa for y. Linear approximations. You did linear approximations on midterm 1, if I remember rightly. So maybe that's less likely to appear on the final. Gradient and directional derivatives. So we need our partials to work out our gradient of our function f. And this is just going to be components equal to the partial derivatives of f. And this gradient vector points in the direction of maximal change, okay? And the length of this gradient tells you the rate of change. So if you're on a hillside and you work out the gradient is pointing up at the steepest angle of descent on the slope. And the length of that vector will tell you the rate of change. Likewise, if it was something like temperature, it would tell you the rate of change of temperature. But if we want to look in an arbitrary direction for a unit vector u, remember u has to be a unit vector, so you might need to rescale it. If we want to look in an arbitrary direction, rather than say looking straight up the hill, we're looking, say, a little bit off to the left or the right or down the hill, then we need to take the dot product between our gradient vector and that unit vector u. Again, just to emphasize that u needs to be a unit vector, so it has length 1. We talked a little bit about the minimum max of a function. Here are partials. All of our partials need to simultaneously be equal to 0, okay? Don't just have one of them equal to 0. They both have to be equal to 0. And we can do something called the second derivative test, where we look at our partials with respect to x and y in 2 dimensions. The second order partials. And the sign of this d, along with the signs of maybe our f sub xx or f sub yy, will tell us something about whether we have maxima or minima for our function, okay? Constraint optimization. You've already done that on an exam, so maybe that's less likely to appear on exam. I'm going to skip over that. And least squares linear regression. So you haven't done that on an exam, so that might appear. See, this is why you come to the review sessions, right? Okay. So remember, for least squares linear regression, we have an equation. If you want to fit a straight line to a set of data, y equals b plus mx, that's our line of best fit. How do we work out this b and this m? It turns out that this is essentially just finding critical values. You don't have to worry about how you get to that process. All you guys need to know is if you have some data points, so some x's and y's, like an x1, x1, y1, if I can do it correctly, x1, y1, x2, y2, and so on, that we can find the gradient by taking the product of our x and y's, so that would be this times this plus this times this and so on, and then take the average of those, subtract the mean of x times by the mean of y, divide by the mean of the squares minus the square of the mean of x. Remember that these two things here are not the same. If they were the same, you'd be dividing by 0. And we know that our line of best fit has to pass through our average x and y values. So that means we can rearrange this equation with our mean of x and our mean of y, and substituting our m value as well. And that'll give us our m and our b. And then we can use that to extrapolate or interpolate values that we don't have in our data set, okay? And then finally, estimating volumes of a solid. So suppose we have some solid, it could be, say, like a log, or it could be an organ, and if we want to work out what the volume of that solid is, we can use the midpoint rule, where we estimate the area at a particular cross-section. If we have measurements at equal values of x, we take this delta x, the distance between those, and multiply it by the sum of those areas, however many we happen to have. So we can estimate the volume of a solid by taking those cross-sections, various points, multiplying them by the distance between those cross-sections. We talked a bit about integration in 2D, as well as volumes of revolution. Volumes of revolution you've already done. Just remember, what we're doing here is we're taking the square of an exterior of a surface as rotational symmetry, and the square of the internal part, if it has a hole in the middle, square those, we take derivative with respect to x. Reason I mention this one here is that in the midterm 2, lots of people did miss off this dx at the end. So if you're talking about integrals, don't forget to have this dx at the end, or dy, whatever you're taking an integral with respect to. But you did do volumes of revolution in midterm 2, so that might not appear on the final. Okay, because we lost a bit of time today because of the fire alarm, let's try and get through some of these problems. So I've got one on here on critical points, one on data fitting, and one on volume of a solid. Let's start with this critical points one here. Okay, so here we're told the fitness of a particular species of owl is given by some function here, depending on x and y. We're not told what these traits are, but there's some traits that have real values. They could be positive or negative. We're asked to find the critical points of f and hence determine if there are values for which fitness is maximized. Okay, and here we've got this description of the second derivative test, where depending on the sign of this d, I mentioned at the start, as well as the sign of this partial potentially evaluated at my critical point, that will give me, that will tell me whether we have a local minimum, local maximum, and so on. Okay, so let's have a go at figuring out, first of all, our critical points. So our critical points, well, first we need to work out our partial derivatives, okay? So f sub x of this function here and f sub y, and set both of those equal to 0. Okay, so when is this, you take the partial of this with respect to x. So this is going to be a constant, this is going to be a constant. And then you could expand this bit out in the middle. If you struggle with doing things like chain rule or product rule and so on, make sure you expand things out, okay? I could expand this out and I'll get 400 minus 40x plus x squared, if I've not made a mistake there. And then take the derivative with respect to each of those things, okay? If you find that easier rather than doing the chain rule, then do that. If you use the chain rule here, the 2 comes out the front. 2 times 20 minus x. And partial for y. When we take our partial with respect to y, now the first term this constant drops out in both of them. The first bracket with an x in, that drops out as well because there's no y's here. And so we're just taking the derivative of this last thing here in the brackets with respect to y. Again, you can expand that out if you want to, or you can bring the 2 to the front and do y minus 12 here. Sorry, we should have a minus in front of that. I think we should have a minus as well here. I think that's right. We have a minus that comes out the front, but we also had a minus outside the brackets. I think both of these should be negative. Okay, so we set both of these equal to 0. So when is f sub x equal to 0? Well, that's equal to 0 when x is equal to 20. F sub y, when is that equal to 0? That's when y is equal to 12. Yeah. Oh, that's because that's why it's wrong. Sorry. That should be a y minus 12 there. And then, oh, I was right the first time. There's no minus sign here, is there? That cancels out. Thank you. Okay, so we find the value for which our partials are both equal to 0. Here, there's just one of these. You might have multiple ones, multiple of these. Just be careful that if you find like a list of ones for, say, values of x and y for which f of x is equal to 0, you need to plug these in to the second one. In this case, there's only one, so we didn't have to do that. But just be aware of the combinations. If you're not sure whether something that you've got is a fixed point or not, sorry, a critical value, all you need to do is you need to take that critical value, whatever it happens to be, some AB, and just look at what is f sub x at AB and what is f sub y at AB. If both of those are equal to 0, you substitute them back in. If both are equal to 0, it is a critical point. If you find that one is non-zero, then you've made a mistake. Okay, so you can do a self-check at this point. Okay, so we want to do the second derivative test to find out if this is a maximum or not. And that means we need to look at our second order partials. That means we take f sub x and we take the derivative with respect to x, which is going to be minus 2. So this is going to be a constant. So we have minus 2x, which we take the derivative of with respect to x for that. So we get minus 2. Do the same for f sub y. Take the partial with respect to y. We're going to get minus 2 from there as well. Why is that? That's because this constant term here drops out. We had minus 2y, so we just end up with minus 2. When we take the derivative with respect to y, we need one more partial, and that's the cross derivative. And it doesn't matter whether you do the partial with respect to x, then y, or the partial with y, then respect to x. For everything in this course, all the functions that you have met, this is always going to be the same thing. And if we do that for either of these, we end up with 0. So then we look at our d, which is f sub xx times f sub yy minus f sub xy squared. We have minus 2 times minus 2, which is 4, minus 0. This is 4, so this is positive. So now that I've got this value, I can go back to this table up here and look at when is my d positive. D is positive in these top two cases here. So I either have a local minimum or a local maximum, but I now need to look at the sign of my f sub xx. 2 seconds and I'll get to you. My f sub xx is negative here. So that means that I am, in this case B, so I have a local maximum. So you had a question. Sorry, why is what not negative? As in the first partial, this one, because we had a negative sign up here, so I believe they cancel out. I think this is correct. I'll double check this afterwards, just because we're short on time today. I appreciate I'm kind of rushing through this, but I want to make sure that we get through a breadth of problems. I'll double check that I've not made a mistake afterwards. If I have, I will correct it. Okay, so here we had our f sub xx is negative and our d is positive. Which tells me that we have an absolute maximum. It's a local maximum, but there's only one critical point, so it also has to be an absolute maximum at 2012. Okay. So when x is 20 and y is 12, this owl's fitness is maximized. Whatever those x's and y's happen to represent, they could represent what type of food it eats. It could be a size of food it eats. It could be something to do with its body size. It could be something to do with where it moves or when it nests and so on. Yeah. Yeah. There will definitely be some interpretation questions on that. I'll try to introduce them into most of the questions, so it won't just be on the new material. It would be, you know, if it had been this question, for example, I might say, if I had said that, if I'd given some meaning to these trait values to, rather than just x's and y's, if I'd said like height and weight, say, and then I would say, tell me when, but what types of owl is what types of hours fitness maximized, then you could say, in this case, it would say have a height of 20 centimeters and a weight of, sorry, not 12 kilos, but you get the idea, right? You then go back and you'd interpret to what does this, because there is always, you know, we do this mathematical step of finding, okay, I found the absolute maximum of this function at this particular point, but then what does that actually mean in terms of height and weight? So often it's actually a lot simpler. I think a lot of students overcomplicate this step of the interpretation. Literally, a lot of the time it's just going back and stating what these x's and y's or whatever it happens to be mean in the context of the original question. Okay, a good question. Okay. I'm going to skip the data fitting unless we have time. I want to make sure that we recap this idea of volumes of solids when we're estimating things, okay? The data fitting question, if we don't have time for this, again, the solutions will be online. All you're doing here is you're putting these values here into our functions for the gradient, which was here at the start. You calculate the gradient and then you calculate the intercept, okay? That's an exercise for you guys to do. We're pretty not going to get that. Let's focus on the volume of the solid and how we can estimate this. So we're going to use the midpoint rule with n is equal to 4. So that's telling me we're going to have 4 cross sections through this particular solid to estimate the volume of a log. And these cross-sectional areas are given in this table below, okay? So when x is at 0 meters, so at the start of this solid, the cross-sectional area is 0.8 meters squared. And then we go along each of these different values, and that will tell us what is it looking like, the cross-sectional area as we move along, okay? So one thing you might want to do is you might want to plot at some distance x along this solid, what is the area at x? Okay, so here we start off at let me change my color. We start off at 0.8 meters, and then we go up to 0.82, a little bit higher, 0.9, 1.02, 0.6, 0.7. This is just a sketch at the end of the day, right? It doesn't have to be perfect. 2. something like that. Okay. And then these are taken equal intervals from 0, 2, 4, 6, 8, 10, 12, 14, and 16 meters. We want to estimate this, and we're told to use the midpoint rule with n is equal to 4. So how do we do that? Well, that means that we need to have groups of 3 points, right? We're using the midpoint, so we're not using the left-hand side or the right-hand side, we're using the middle point. So we're looking at this in groups of 3. So that means that I ignore this first one here. This is going to be my right-hand side. This is going to be my middle. Likewise, this 6 is going to be my midpoint, and the 10 and the 14. On my diagram here, what that means is the height of my rectangles, and I'm estimating this, is going to be given by that midpoint. It's going to be given by this midpoint, and by this midpoint, and by this midpoint here. Then we can draw those rectangles, and we can name each of these areas as just being A1, A2, A3, and A4. So how now do we work out the volume? Well, our volume is going to be approximately equal to change in x, so the distance between each of these cross-sectional measurements, times by the sum of whatever those measurements are. So here we're going to have I is equal to 1 to 4 of these AIs. What's our delta x here? Can anyone tell me? So x, this is the total length of the object is 16 meters. Our delta x is the distance between each of the cross-sectional measurements. Anyone? 4, yeah. Okay. So 4 meters. Now we just substitute these things in. So we have 4 meters times by, and then we read everything off the table, things that I've highlighted. So 0.82 plus 1.02 plus 0.87 plus 0.7. You work that out, should be 13.64 watt. Meters cubed, thank you. Don't forget your units if you're dealing with volumes. Okay, so we did also discuss earlier in the semester other ways of constructing estimates for volumes, and they could have been the left point rule. So if I was using the left point rule, then that means that the height of these rectangles would have been determined by the point on the left. So they would have looked like this instead. Likewise, we could have done the right point rule, in which case the height of the rectangles would have been determined by the point on the right-hand side. We usually use the midpoint rule because that tends to be a better estimate than using the left or the right. Okay. Any questions about estimating the volume of solid? Nope. Okay. We've got just enough time to whiz through this question, I think. So here we've got 3 data points, and we want to plot a line of best fit using least squares regression. So that means I just need to plug these in. This would be a good one if you have a calculator. So maybe I might put calculators on the final, we'll see. Okay, so we need to take, first of all, the average of our x values. So here, there are 3 points. So we're going to divide by 3 and then sum up the x coordinates, which are going to be 1, 3, and 5. That comes to 3. Likewise for our y's, our average y value is going to be divide by the number of points, in this case 3. We have 2, 4, and 3 here, so we're going to divide by 9 by 3 again, so we get, 9 over 3, which is 3. So those ones tend to be straightforward. This is where people often make mistakes, the X, Y mean. What we're doing here, again, we've got 3 points. We're going to divide by 3 at the front. For each of our data points, you take the product within that data point, okay? So you take 1 times by 2 plus 3 times by 4 plus 5 times by 3, which should work out to 29 over 3. We then have the mean of the squares and the square of the mean. These are the things that appear on the bottom of my gradient. So the mean of the squares, so that's where we have the bar over the top. You can think of this almost as being like a little brackets underneath the bars, if that helps, okay? So we square each of our x coordinates, and then we take the average of those. So we have a third times by, what are my x coordinates? Well, that's 1, so we will have 1 squared. We have 3 squared, and 5, we have 5 squared. So if you work that out, you have 1 plus 9 plus 25 in the middle, so that's 35 over 3. The last thing we also need to work out our m is we need to have the square of our mean. So here we have our x bar, which we've already worked out, and we square it. That's just going to be 9. How do we work out our gradient? Well, now we've got all of the components we need. We just need to put them into the formula that we're given. So we have xy bar minus x bar times y bar divided by the mean of the squares minus the square of the mean. In this case, we have 29 over 3 minus x bar times y bar. So yeah, it's just 3 times by 3. Mean of the squares is 35 over 3, and the square of the mean is going to be 9, which I'm actually going to write as 3 squared. The reason I'm going to write that as 3 squared is because we have lots of 3's in here, so we can do some cancelling. If we do some cancelling, we're going to have 29 minus, let's see, we're going to get rid of this 3 here, and this 3 here. We need to then multiply this by 3 and this by 3. So you have 29 minus 3 times by 3 times by 3, which is 27. 35 minus 3 squared times by 3, so that's 9 times by 3, which again is 27. We're going to have 2 over 8, or a quarter. See, who needs calculators? Okay, how do we work out our intercept? Our intercept we work out by remembering that our line of best fit goes through our average values, okay? So we take B, our intercept is equal to our average Y value minus M, which we've just worked out, times by our average X value. And this is just substituting things in. So what's our Y bar was 3, our M is a quarter, and our X bar is 3. So this is 9 over 4. Okay. The last step is then to actually plug these in and write down what your line of best fit is. Don't forget to do this. Again, this is something that students often forget to do, is they'll maybe work this out and work this out, but not actually plug it back in. So we had our y is equal to b plus mx. So our y is going to equal 9 over 4 plus a quarter of x. You can then use this value to interpolate or extrapolate other values, assuming everything is linear. Okay. Sorry about the distraction today, guys. We had to rush that. I'll see you on Wednesday.